Greetings everybody. This is the last video for Exam 2 Practice 1, and it's a bonus question, and notice here it's a UCM problem. So you have this toy. It consists of a small wedge with an angle of theta. The wedge is frictionless, and you can spin it. You've got this vertical rod attached to the bottom of the wedge, such that you can spin it. And if it's spun at a certain speed, the wedge will remain at a fixed distance L along the wedge. So if you spin it at a certain distance, that mass M will not move. But what's happening is when you spin this wedge, the mass M moves, it undergoes UCM in a horizontal circle. We'll show that this speed is given by the expression V is root GL sine theta, where G is gravity, 9.80 meters per second squared. L is the length from the mass to the edge of the wedge in meters, and theta is just a sine of the M. We just want to show that that speed is given by that expression. And it gives you a hint. Break the normal force acting on that mass. Break the normal force into its x and y components. The x component will be in the radial direction. Then apply Newton's second law for UCM to the mass of M. Then apply Newton's second law in the y direction. Then apply some basic right triangle trigonometry. So let me go ahead and what does this mean? We'll break Fn into its x and y components. And let's go ahead and remember, this little this mass M looks like a little tiny hockey puck or coin or whatever. But that mass M, that's what's undergoing the UCM. As you spin the wedge, that mass will be undergoing UCM in a horizontal circle. Let's look at the solution. Well, here's my sketch, and what I want to do, here's the mass M. I want to draw all the forces acting on the mass M. Well, there's the weight, mg, pulling straight down. Now there's the normal force, Fn, that's the force of the wedge on the mass. Now notice again, I've taken great care that the green normal vector Fn, that vector is clearly perpendicular to the wedge, i.e. to the incline. Now then the hint says, once you draw Fn, break it up into its x and y components. Basic trigonometry. And again, it's easy to show that if the angle of the wedge, i.e. the incline, if you want to call it that instead, it doesn't matter. But if this angle here is theta, this angle, as I've drawn here, is also theta. And Fn is the hypotenuse. Well, again, the x component is Fn sine theta because it's opposite. So the blue vector, that's the x component of Fn. And that's sine theta because it's opposite. The y component of Fn is Fn cosine theta. So that's what I've done. I've taken Fn and break it up into its x and y components. Notice the x component, Fn sine theta, it's in the radial direction. As you spin this wedge, the mass M will move. It will undergo UCM in this horizontal circle indicated by that little dash, or little line, the little dotted circle here. So the mass is moving it's undergoing UCM in a horizontal circle of radius small r. So Fn sine theta is in the radial direction. It's pointing towards the center of the circle. So let's go ahead and let's apply Newton's second law for UCM, and then apply Newton's second law in the y direction. Well, notice of these forces, I have one in the positive y, one in the negative y, and one directed towards the center. Well, Fn sine theta, in terms of the radial direction, is positive. It is directed towards the center. So Fn sine theta, that's the radial force, that's equal to mv squared over r. That's Newton's second law as applied to UCM. That's equation 1. Now notice, in the y direction, again, remember, you spin the wedge at a certain speed, the mass undergoes UCM. It's in this horizontal circle. Again, there's no acceleration in the y direction. So Fn cosine theta must equal mg. Again, the positives must equal the negatives. It's not moving in the y direction. You spin it at a certain speed, and it undergoes UCM in this horizontal circle of radius r. So I know Fn cosine theta equals mg. And I know that Fn sine theta must equal mv squared over r. Well, I've written those two equations. I wrote them in that order as such. When you take equation 1, take equation 1, divide it by equation 2. So take 1 divided by 2. So left side divided by left side, right side divided by right side. Well, on the left side, you end up with tan theta, because the Fn terms cancel, and sine over cosine is tan. On the right-hand side, the m's cancel, and you're left with v squared over gr. Well, it's trivial. That means v is equal to root gr tan theta. But I want this expression. I want to show that v is root gl sine theta. Well, now we're done with Newton's second law. Now just some basic right triangle trig, so we can get the final expression. Now here, use basic trigonometry to get r. We're done with Newton's laws. This is just basic right triangle trig. Well, here's another sketch. This is the radius r of the circle. Here's your L and your theta. Well, clearly, cosine theta is adjacent over hypotenuse, a over h. So cosine of theta is r over L, which means r is L cosine theta. So go ahead, and in our expression for v is equal to root gr tan theta. Now we're replacing r with L cosine theta. Well, cosine theta times tan theta gives you sine theta. So you get v is root gl sine theta, as you're asked to do. But the key to this problem is you draw the forces acting on m, little m. They're just the weight mg and the normal force Fn. Well, then Fn has an x component, which is Fn sine theta, and it has a y component, which is Fn cosine theta. Fn sine theta, notice where is it pointing? It's in the radial, it's in the positive radial direction, because Fn sine theta is pointing towards the center of the UCM. So you have Fn sine theta equals mv squared over r. Clearly, Fn cosine theta equals mg. We have equation 1, equation 2. This is a standard technique. Divide, just take 1. Equation 1, divide by equation 2. Left-hand side, the Fn's cancel. What's sine over cosine? Tangent. Right-hand side, the m's cancel. You get v squared divided by gr. Solve for v. Then just use trig to get an expression for r. And plug that expression for r into the original answer. L cosine theta. And then cosine theta times tan results in sine theta.